I will tell you when the stream will be started. Hi everyone, and we will start our new lecture. It will be the 5th lecture in advanced track, and your teacher, Mladen, will speak with you and discuss some interesting topics. So I give you the microphone.
Hi everyone again. For those that haven't been here on Thursday, my name is Mladen. I've been a competitive programmer for over 10 years. I've been teaching for over 7 years. I've been twice to the International Olympiad, once to the World Finals, won a bronze at the Olympiad in 2019, and now I'm working as the head coach of the Serbian national team and working with some other teams as well. So today, let me share my screen. Today we will be working with suffix arrays. So yesterday you got this topic unlocked, and not sure how many of you were able to check it out. I know it's a weekend. Thank you for coming today on a Sunday, but we will be you will be receiving a nice, hopefully, lecture around a nice topic. So the topic is suffix arrays. So suffix arrays, that means we'll be working with some arrays, definitely some suffixes, so that means probably some strings, and that would be a good guess. So we maybe know some things with strings already, some hashes, maybe the Knut-Morris-Pratt KMP algorithm, maybe Manaker, some of these different things. And those are all very useful things. However, maybe we want some more to do more stuff with strings. In that case, these suffix data structures are really useful. So there are three big suffix data structures: suffix array, suffix automaton, and suffix tree. I think suffix tree is the oldest one out of the three, and suffix array was created more to simplify, as it's a simpler way to do similar things that suffix tree can do. Suffix automaton is a bit more advanced topic to do more advanced problems. I think it will be one of the topics during the in-person camp in a few weeks. So why is this called suffix data structure? Well, they will be dealing with all suffixes of a specific string. So let's say we have some string. And what are the suffixes? Well, this one, this one, this one, this one, and so on. So all some last characters of the strings, that's a suffix. And why are these suffixes useful? Well, because each prefix of a suffix is a substring, right? And each substring is a prefix of a suffix. So whenever we want to let's say, look at some substring, let's see ACA here, that is going to be a prefix of this suffix. Right. So anytime that we want to do some operations, maybe with substrings, it is going to be useful to consider these suffixes and then their prefixes. So let's go on. So what is the suffix array? The suffix array is actually a sorted array of all suffixes. So lexicographically sorted. So here we can see the same one for the string I mentioned, ABA, CABA. We can see that once we take all of the suffixes which I mentioned previously, sorry, just a second. Yeah, okay, sorry. So we have all of these suffixes, and once we sort them, it will look like this. First, we have all of the ones which start with A, then all of the ones which start with B, and so on. And amongst the ones which are sorted by A, first comes just A, then all of those which start with P, then all those which start with C, and so on if we had more characters. Of course, we're not going to keep the entire strings like this because that would be O of n squared memory completely unnecessarily. What we're going to store is just these indices. Okay, so what does this mean? So the first element in the suffix array is the suffix starting at index 6. Second one starts at index 4. Third one starts at index 0. And so on. And the suffix array would be exactly this: 6, 4, 0, 2, 5, 1, 3. Gerkin asks, what do the letters stand for? I'm not sure I understand. So these letters are all the suffixes of a given string. So we have this string ABA, CABA. And once we take all of those suffixes and sort them, that is what these strings are. So this A is the last character. ABA is the last 3 characters. ABC, ABA, CB, ABA is the whole string, and so on. So all of these are suffixes of ABA, CABA. And once again, once we sort them and take only their indices, this is what we get: 6402513. Let me know if maybe I misunderstood your question, but yeah. So the biggest question now is, how do we build this array? So the idea, what it is quite simple, but it's not that trivial to build. So we know that we need to sort all of these suffixes fast enough, and maybe some of you could build this quickly using hashes. That's fine, but we're going to do it quicker based on constants, and we're also going to do it much easier, and we're also going to use it deterministically without the randomness that each hash has. So we're going to do it without hashes. We're just going to have a deterministic algorithm. So first thing that we're going to do is that we're going to add an ending character to the string. So in this case, we're adding this $sign. This sign, this character needs to be smaller than all of the other characters in the string. So here I have the ASCII table, and we can see here at 48, we have the numbers. Then at 65, we have the capital letters. And then at 97, we have the lowercase letters. We want something that's smaller generally than all of this. So you can use $sign, pound sign, exclamation point, the percent, ampersand, plus whatever, any of these smaller ones. Just make sure not to use like this, because this tilde sign is bigger than all of the letters, so you will have an issue with this. Also like this, maybe don't use the question mark or something like this. So just take one and usually just use that one. The $sign is fine for that. So why did we add this? Well, we added this, and imagine that we also duplicated the string. So instead of just ABA, CABA, imagine that we have ABA, CABA, $sign, ABA, CABA. And now we're going to compare all substrings of a fixed size, here of size 8. So this would be the first one, this would be the second, and so on. And we can notice that this would be the same thing. We would still get, as you can see here, the same array. The only thing is that we now have this just $sign suffix as the first one, but we can ignore that one because that's useless. But if we notice, everything else is the same. First goes A, then ABA, then ABACABA, and this is because we added this $sign. Why did we add this? We'll see soon. And other than that, we want these lengths to be a power of 2. So those are the two prerequisites, and we'll see soon why. So here it's 8, so it's okay. But if it was 7, for instance, if we didn't have this A, we would just add the string again. Okay, and then take 8. So it needs to be a power of 2 that's bigger than the length of the string. Now, why did we do this? Well, we're going to do this kind of iteratively. So first, we're going to sort by the first character, right? We can see that the first character will determine like their groupings, their batches into groups, right? So we have first the A's, then the B's, then the C's. So let's just sort first by the first character. So we would just sort by the first character, and this would be like, however, it doesn't need to be sorted by the other characters, just by the first characters. So yeah, imagine it's something like this. Then we might have like this, this, and this. So we only sorted by the first character. Notice that inside the same character, for instance, these ones which are sorted by A are not necessarily sorted. So we just took basically a pair of character I and just sorted this, okay, by these first characters. So we know which characters have first letter, which suffixes have first letter A, then B, then C. Now what we're going to do, we're not going to now just go, we will go for the second character, but we will not just go one character by one character, but we will double each time. That is why we needed the power of 2. So now, instead of just looking at sort by the second character, this would be as like S of I of 0. So the 0th character of the ith. Actually, yeah, I was correct the previous time. And so on. Okay, so we're going to do it, like I said, in all powers of 2. So we have already sorted by the first one. How are we going to sort now? Well, we're going to introduce something we call a class. It's going to be useful. So a class for K and I, it's going to be the bucket where suffix I is after comparing first 2 to the power of K characters. So what does this mean? So after we sorted by the first character, so class of 0 of I, for these 4 strings, it will be 0. for these two strings, it will be 1. So these ones are the 0th class, these ones are the 1 class, and this one is the 2 class, right? Because we are bucketing here only by the first character. But now what's going to happen when we bucket by 2 characters? Let's sort by 2 characters now. Now it's going to be, let me draw it here again. Now it's going to be sure we can write the other one. So now we're sorting by first 2 characters. I missed one, sorry. So this is just so we can see what these classes actually are. So now, after we have sorted by the first 2 characters, what are the classes? Well, the classes are, here is, we're comparing only first 2 characters. So this one is class 0, but the next one has a different class. So it's going to be class 1. Right? So let's draw a line. But the next one has the same class, class meaning first 2 characters. So it is also going to be class 1. Then we have class 2 for AC. Then again, it's a new class for BA. And finally, the last class for CA. And notice that once we have n classes, where n is the number of characters, we are finished, right? Because we have successfully sorted the strings. Once we have looked at the big enough prefix such that we can uniquely determine the order, we are finished. We have found a suffix array. But other than that, we need to do another iteration with the double prefix. So here, like I said, we're not going to do one by one. We looked at the first 2 characters. Now we're not going to look at the next first 3 characters. We're going to look at the first 4 characters. How do we do that easily? So we're not just going to compare strings. So notice, for instance, if we wanted to compare these two, so ABA, like this, and ABA $, ABAC. Let's say we wanted to compare these 2 strings. How would we do that? Well, we know that they have the same class for the first 2 characters, right? So we want to have like a tiebreaker. Well, what's going to be the tiebreaker? Well, the next 2 characters, if possible. Maybe they are also the same. Here they are not, but otherwise maybe they are. But what we can notice is that when we look here and here, those are going to be different suffixes, right? This is the suffix of length 3, but if we remove the first 2, it's going to be a suffix of length 1. So now what we need to compare is this suffix, right? And this suffix. And which one has a lower class? Well, this one. So this string would go first. So we would need to swap them basically. So what are we actually doing? When we're looking for the first 2, when we're sorting by first 4 characters, we're looking for the class of the first 2 characters. Here for both it's going to be 1. And here for this one is going to be 2 for the class of the second 2 characters. And it's going to be 0 for the class here of the second two characters. So what does this mean? After we sort this by pairs, we are done. We have now sorted by 4 characters. After that, we're going to double. We're going to look what's the class for the first 4 characters and what's the class for the next 4 characters. And now we're going to sort that. And basically we'll do that until we get the sorted array and n different classes. So we'll get around to the code. I would like to talk a bit more about the idea first. So let's kind of write a pseudocode, like how we would do this. So first, let's add, first step would be add $sign to string. That's simple. After that, calculate the first class. So C of 0 and for each I. After and sort by first class. Or that would be, I guess, in the opposite order. But if we calculated the first class, we have already sorted by the first class. So this is, I guess we can show the code a bit. So this is what we're doing here. So we're adding, let me zoom in a bit. We're adding $sign here. We're here getting these pairs of character and index. We're sorting them. And this is the class 0 of C0 of I. So we're going with the first class is 0, and then if they are different, if this character is different than the previous one, then the class increases. So this was like the first class which we did, only comparing by the first character. So the first class is 0, but if the first character differs, we increase the class by 1. Okay, so we have found the starting classes. After this, we're going to do while 2 to the power of k. We have some k which starts now at 1. And while 2 to the power of k is smaller than n. And what we're going to do? Well, we're going to do very similar. So calculate, this would be like 3.1. Calculate the pairs. By pairs, what do I mean? So if we're looking at the first 8 characters, that means the class of the first 4 and the class of the second 4. That would be the pair. So we can write it as C of k minus 1 I and C of k minus 1 I plus 2 to the power of k minus 1. And this is going to be modulo n. And this would be the pair which we would compare. So what is it called here? It's just called TMP, like temporary. Okay. So what this is exactly like what I mentioned, the class of the first half, class of the second half. So in the previous step, if now we're doing 2 to the power of 3, which is 8, that means in the previous step, so if this is 8, and we want to calculate it for I, we want to do I4, and I plus 4 and also length 4. What is this modulo n? This is to do what I mentioned at the beginning, but we didn't really do, which is to add until we have enough characters to loop it. We don't actually need to do that. We can just always modulo the indices by n. And that's the same thing. You basically get a circular string, which is infinite. So we don't need to worry about duplicating, tripling the string. Just we need to make sure that whenever we increase the index, that we use modulo n. But yeah, okay, calculate the pairs, sort the pairs, and calculate new classes. So in this case, it would be class of k of I. So for each I, to calculate the class of first 2 to the power of k elements. And now we can add additional step. If we have n classes, break. Okay, and this is basically the whole idea. If you have any questions about this algorithm, make sure to ask them about the idea. We're just going to go through the code a bit. Then we talk about the complexity and how we can improve it. So yeah, let's go on to the code and I'll be checking questions if any arise. So we talked through this part already. So add the $sign, calculate the first pairs, sort by first pairs, then calculate the classes. So now we have these first classes. Those are the first two steps. After this, we're doing the third step. How do we sort it? I think that will the code will help with that. So again, like I said, we're going with k here, and it's similar. So you can notice here it's just 2 to the power of k plus 1 less than 2 times n. It's the same thing as here. And we're increasing k. So we're generating here new pairs. And this is what I mentioned. So it's class of I plus 2 to the power of k. It's a bit shifted because here I indexed from 1, they indexed from 0, but it's the same thing. So it's C of I plus 2 to the power of k modulo n, and we always need to keep the index as well to know what index does this pair actually represent. And after that, we can literally just sort this temporary vector. How is it going to sort it? Well, because these are pairs, it's first going to sort by this. So means it's going to sort first by this, by the previous class. So if something that we sorted previously, it's not going to get corrupted. If we sorted it good, it's going to stay good. We're only going to sort it more precise now by checking double the characters. So if previously 4, now 8. So that is how the sort works. So this is the classic C++ sort. Then we do the classes. So we set the class for the first element is 0. And then we go through the entire temporary array. And if it's different than the previous element, that means it gets a new class. So we increase the previous class by 1. And in the end, this is step 3. If the maximum in the array is n minus 1, that means that we have n different classes. which means that we are done, right? And we can break. And in the end, just to generate this suffix array, we're going through all the different positions in the classes, and we're saying, okay, the suffix of C of I is I. I guess it didn't explain this on the board, but basically means like which string has class 0? Well, that string is the first element. Which string has class 1? That is the second element, and so on. So just to stop here for now, Gherkin, how do we sort it? Is it clear now with code, or should I maybe explain something again before we go on to the complexity? Anyone else, of course, if you have questions, make sure to ask. To explain again. Sure, let me explain it again shortly, but please make sure to mention exactly what part you didn't understand, to make sure I don't explain everything needlessly, but here I will, because it's okay. Let me see just where to start. Let me give an overview. So again, we want these sorted suffixes of a string, and how we're going to do it is by doing first comparison of their first string of each first character of each suffix. Then we're going to compare the first two characters of each suffix. Then compare the first four characters, then 8, and so on, until we are sure that we have split them. Okay, lexicographical sort. I assume that maybe you have heard it before, but I can explain that really quickly. What is lexicographical sort? Lexicographical. So this is a way to compare strings. Basically, if you have string ABA, CABA, the same one, let's say, and we have ABC, C, or AC, whatever. What does lexicographical sort mean? That means we're going character by character and sorting, seeing if there's a difference. So we're first comparing the first character, A and A, they're the same. So we go on to the second character. B and B, they're the same. But now we look at the third character, and we see that A is smaller than C, which means that this first string is smaller than the second one. So lexicographical sort means we're going left to right, and in the first place where they differ, we select the one which is smaller. In case they're not the same length, let's say we have like ABA and ABAC, this one is again smaller. The one that is shorter will be smaller. But of course that is also done by adding this $sign, so we always compare of the same size, so we don't have to worry about this. Yeah, no problem. So this is why this lexicographical sort is useful here to understand, because this is what we're doing, right? We're comparing first by the first characters, then by the first two, by first four, first 8, and we're only getting more specific, right? If the first character is A and for some other string the first character is C, they will never swap later. But maybe within all of the strings which have the first character A, we can sort them better or more correctly. So that's why we're adding more and more characters. So to go through the code again, here we're first calculating the first class. So we get the pair of character and index. Then we sort those, and now we know, like, sorted by only the first character, what would that look like, the indices. So we give them the classes. The first, that presumably starts with an A or whatever the first letter is, it's 0. Then we go on to the second, third, and so on. And as soon as they differ from the previous one, we increase the class by 1. So these classes are kind of like groups with the same prefix. So that is why they're useful. After we have done that for the first character, now we want to do it for the first 2, first 4, and so on. That is this for loop. So we start here, in this case, from 0, then we go on till it's big enough, and we calculate the pairs. They're these pairs. So this is the class for the first 2 to the power of k elements, and this is the class for the second 2 to the power of k elements. And once we put those in a pair, we can imagine that as kind of a class for the first 2 to the power of k plus 1 elements. So we doubled the size by using the class from the first half and class for the second half. So now we sort using that, this whole vector. And now we have these indices again sorted even more precisely. And now we calculate the new classes. So again, as with the first character, the first one would be 0. Then after that, each time that we see a difference, we increase the size by 1. If we have n classes, we can finish because we have completely sorted them and there is no more precision needed, and we can just get the suffix array. Okay. So what about the complexity? Well, we know that each sort, yeah, Gerkin, which type of problems we will be using it? Yeah, we will be talking about that in the second part, don't worry. Let's just talk a bit about the complexity. So we know that we can sort characters in n log n, right? So each of these built-in sorts is n log n. And in this loop, we have log n iterations, right? Because this k, sure, it increases by 1, but what we're actually considering is 2 to the power of k plus 1, right? So that means that we will have log n iterations because each time we're multiplying by 2 what we're considering here in the condition for the for loop. So the total complexity is O of n log squared n, right? N log n log n. This is the same solution as we would probably get with the hashes, but it's much faster, a smaller constant factor, no randomization, and so on. And in most cases, this will be perfectly enough. So there is no reason to do anything more than this. Just do this and you should be fine. That's all. This is the most part, but we're computer scientists. We want to try something better. Can we do it? Yes, we can actually do much better. So let's first look how to get rid of this log n from the sort. So yeah, this is the sorting optimization. So we want to get the entire algorithm to n log n instead of n log squared n. How can we get log n out of the sort? Well, we know that we cannot use any comparison sorts faster than n log n. That is not possible. That is mathematically proven not to be possible. But what we can actually do is use something called counting sort. That's a different type. That's not a comparison sorting algorithm. So we're going to use that to get rid of the log n. So what we're going to do is, because we need to sort these vectors just to do it quicker, we're going to use first counting sort over the first element of the pair, then counting sort after that on the second element, or yeah, okay, it's not related. So yeah, we're actually going to sort first by the second element of the pair, and after that we're going to sort by the first element of the pair, and like that we're going to get the answer. So because all of these ones, C of I will always be at most n minus 1, even less actually. So we can use a counting sort where we need an array. So we add an additional array here, and then we count like how many times we have seen it. Do all of this. So this is like classical counting sort. I would not spend too much time on it. But the whole idea is that because we're sorting pairs, we would first do it on the second part, then on the first part, and after that we have the sorted array of vectors, of pairs, sorted vector of pairs. And after that, you can look at the code maybe later if you're not too familiar with this. But after this, we have n log n complexity. Like I said, this should not be used often. And the thing is, we can actually do even better. There is an O of n algorithm. It is linked here. If you really want to learn it for some reason, you can go and read this document, this scientific paper. It's interesting. There are many actually, much work done on the suffix array. It's a relatively new data structure as far as data structures go. It was only created in 1990, and some of these new, I think the linear algorithm was only given like 15 years ago. So that is considered quite new for a data structure. So yeah, if you want that, or if you know suffix trees, you can build that in linear time and construct a suffix array from this. But like I mentioned, our algorithm is enough, even the log squared n. This is more like a fun alternative. So after this, we'll have now a short break. After the break, we will look at some applications. So number of, we'll see. So there are 3 to 6 different applications we will talk about depending on the time, on how we can use this, and this is quite useful. And even maybe if you didn't quite understand all of the details of the implementation, that will not be too bad for the second part. So stick around. I think you can still understand how to use it, and then maybe you can go back later and learn, refresh how you would build it. So
Okay,
yeah.
so now we will take a break for 5 minutes. And could you please write the time? Yeah, please. So see you in 5 minutes, in 5:50. Yes, 5:50 p.m. See you soon.
Let's continue.
Yeah, let's start.
Okay, so let's now talk about the applications. Good thing about suffix array is that it's often very simple once you uh, do a lot of problems in it to recognize when it's used. It's one of those things when it's where it can be pretty obvious, like when you need to use it. So let's go through a few applications. First, one of these is simple. So first one is substring in a string. So if you know like the Knut Morris Prat, or if you've done hashing or something like this, you have done this probably. So this is like you have a S and T and check if T is a substring of S. And KMP and hashing does this in O of S plus O of T. And this is all fine and well. However, in case we have many T's, that is going to be slow because each time we would need to go also through S. So if we have many small T's and one big S, that's going to be very slow because for each small T, we need to go through the entire S. So we don't want to do this. What we can do is actually just build a suffix array for S. Okay, so we get suffix array for S. And what we do then? Well, we just do binary search actually. So we would, what would we do? So let's say you get again, let me use this one again, this ABA, CABA, and let's say you want to check whether ABAC is, or let's use BACA. We want to check whether BACA is inside this string ABAA, ABAC, ABA. So we're going to do a binary search on this suffix array. So we would get this middle one, which is this ACABA. And we would check like, does this compare? Is this a prefix? And immediately we see no, right? This differs. But we know that it is smaller than this. So now we need to go to further elements. So elements below this. So now we would check like BACB, CABA and find it, right? So just do literally a binary search to try to find it. What would be the complexity of this? Well, we only have like O of S log squared S for the building of the suffix array. And after that, we have T log S. So log S because of the binary search and T because of the checking, like because we need to go to at most length T to find whether it is compatible. And if we have multiple T's, we can just do the sum over them, but it's still going to be much faster than previously because this was our limiting factor because we would have like M times S, which would be too big. So this is like standard first application for suffix arrays. And we will often do these binary searches to find exactly the placement. But let's go on to a bigger topic, which will be used for all further things. Actually, I wanted to mention one thing which I forgot. If we don't put this $sign and still do the same algorithm where we're checking first first element, then 2, then 4, then 8, but we don't put this, what's going to happen? We're actually going to sort all cyclic shifts of the string. So what are cyclic shifts? That would be like, this is the first one, and then you take some elements and move them to the end. So let's say like this would be a cyclic shift of this string. And if you wanted to sort all of them, you would do the exact same algorithm. You would just not put the $sign at the end. So that is also useful sometimes, even in one of these tasks, one of these labs. Okay, so for all of these next ones, we need a bigger topic, which is this LCP array, which is the longest common prefix. And this is basically considered almost one thing with the suffix array, because this is so useful. For most problems with suffix array, you will need this as well. And the code is very short, so you will not have an issue to code it, but it is a bit tricky to understand. So let's first define what it is. So after we get the suffix array, we get something like this, right? 764025113. And this would be the suffixes that represents. The longest common prefix array is exactly what the name says. It's the size of the longest prefix for each 2 consecutive suffixes in the array. So the longest common prefix between this and this is 0, but between this and this it's 1. Between this and this it's 3. Between this and this it's 1. This and this is 0. This and this it's 2. This and this is 0. And we'll see later why this is really useful. But let's try now to calculate it quickly. It's not that simple, but it is quick. So maybe the first thing that you would try is just to go down this array and try to calculate it. But this would be hard, because there is nothing that really help us not just start from the beginning each time. So to start here and compare, then start here, then compare, then start here, then compare. That's going to be slow. That's going to be n squared. We would actually want to do it in another order, such that we have the benefit of starting someplace else. And what order we are going to do? We're going to start from the longest suffix and its element, so this 3, to the shortest one, so this empty one, or I guess this, which contains just a. So that is the order which we are going to do, which is also the order of going through the string left to right. Okay. So let's look at this. So for the longest one, we have ABA, CABA, and the one above it is ABA, ABA, ABAC. Okay, and here we would do the brute force. So just go left to right and calculate that it is 3. Okay. This is important. So the first one is brute force. But let's try to use these three in a smart way so that we don't have to start from the beginning on the next step. Okay, so what would be the next thing which we are trying to calculate? Well, the next step we would like to calculate is, what's the second longest one? It's this BACA dollar sign A, and the one right before it, right? So so notice that this one, the lower one, which we are iterating over, is just this with the added character, but that character doesn't really matter because it's after the dollar sign. But these two are the same. So if in some crazy case, this one was the same as this one, we know that we could start just from 2. We know that the first 2 would be the same because here the first 3 are the same. And if we removed these ones, then we can just start from the third one and try to compare, right? Does that make sense? I think that that is reasonable. But what are the chances that those two are going to be the same? The one before this one and the one before this one to be again one after the other. It's possible. It's maybe even not that rare, but it's not going to be always the case. But what is going to be always the case, and this is really interesting, is that this one is going to be before this one in the suffix array. Whatever this one is. Actually, okay. Here it did actually happen that they are the same, right? I just realized that. Yeah, they are the same in this case. So we know that we can continue here from does the second one and see that it is 2. But let's take a look. Yeah, we can, let's do another iteration. So now what is the string that we're doing it for? It's going to be ACABA dollar sign A B. All right, so this is the third longest suffix. But what is the one before it? It's this big one. BA CABA dollar sign. So like I mentioned, this case now it's not true what was true in the previous one. So sure, this one again, of course, is the same as this one. That is how we selected it. But in this case, this is not this, right? So here we do not know that we can just start from the second element. We might need to start from the beginning. Well, no, because like I said, this one, just a second, this one is going to be before this one in the suffix array. So this one is before, this one is after. I'm talking specifically about this. And we can see that this is the true here, because here, this is here and this is here. So this is before this in the suffix array. But why is it always going to be the case? Well, because obviously these two were the same. So this one here was before this one, right? So it's before this one. And this one is right before this one. So can I? Oh, I can draw here. Awesome. Um, yeah. Uh, so like I said, this one, we said that that one is after this one. And this one is right before this one. So because this one is before this one and this one is right before this one, that means that this one must be before this one. I'm hoping that you're seeing the lines I'm drawing on the on YouTube as well. So this is just like the positions of these need to make sense. So we know from here that this one is before this one, and we know that this one is right before this one. So at the end, again, to repeat, this one needs to be before this one, or at least the same one, which was in the second iteration. Okay. So what does this mean? It means that here again, we can just start from the second one. Why is this the case? Well, if actually this was the case, but that's fine. So now this part is easy if you understood so far, because if this one and this one have a common character, then this and this one also need to have that many common characters. Does that make sense? I think it's reasonable, right? Because again, we sorted these lexicographically. If this and this have some common prefix, here A, all of the ones between them also need to have that prefix. So again, we could just start from the previous one minus one and continue from there. Now, why are we doing all of this? We're doing all of this to have good complexity. Let me stop the annotation. Actually, let me delete the annotation first. Right, so this is kind of what I was drawing previously. So if this one and this one have a common suffix, a common prefix of size k minus 1, then this one will also need to have that same prefix. And the code, like I said, is very simple. We start from 0 as the brute force, like I said, and we compare. We increase this if they are the same. But this is the most important part. This is what I was talking about. That we, from the next time, we start from k minus 1 instead of starting from 0 again. So in the first one, we compare and we start 1, 1, 1, 1, 1, right? But for the next iteration, we only need to start from k minus 1 instead. And in this case, this would greatly reduce our complexity. Why? Otherwise, it would be n squared. Now it's actually all of n. I know it looks weird because we're here increasing a lot. But what's the thing? Well, k, how long we're going, can be at any time at most n, right? This k from the code, which is how far we're going, how far we're doing this comparison. So this would be k. So k is less than n. and we're decreasing it at most n times, n minus 1 times actually. So the total time that the total number of times that we can increase it is 2n. So total number of increases of k is at most 2n. So the complexity is O of n. I still have some annotations on my screen. Hopefully they're mostly gone. So yeah, it's a very short code. Again, like if you have any questions, you should ask them now. Of course, it's good to go over this again offline. This is written in a much more detailed way, definitely. And this is called Kasai's algorithm. I forgot to mention that. So it's good to know the names of these things. So Kasai's algorithm. So yeah, go through these images, the code, or you can ask a question now to help resolve it. Again, if you want to later go back, but maybe you didn't understand now, you don't want to ask a question for some reason, that's okay. We just need to know what, yes, the LCP is longest common prefix. So we just need to know what it is to go on onto these last three applications. Okay. So just know that the LCP is the longest common prefix between two consecutive elements in the suffix array. I'm not seeing any other questions, so let's go on to other applications. So if we wanted to find the LCP, the longest common prefix of some two random suffixes, so not necessarily consecutive ones, well, what would we do? Well, we would just find the minimum on an interval. So what does this mean? Again, let me share here. So let's say we wanted to find the longest common suffix between ABA and ACABA. That is just going to be the smallest of the LCPs between those two. So in this case, it would be 1, and we can see that is true. So A would be the longest common prefix. If we wanted between ABA and BA, we can see that 0 is the minimum one between those, and that is true. They don't have a common prefix. So that is the case. Why is this the case? Well, it makes sense, right? So sure, we might have some big LCPs here, right? Even ABA and ABA like here, length of 3. But as soon as we have a 1 here, that means that we lost all that after, right? That is not useful anymore to us, just that 1. Even further, if we go, we've lost even that 1. We're back to 0. So how do we get the LCP of two any suffixes in the string? We do a range minimum query. So just to find the minimum of some interval. So how do you do that in general? Either like you use a segment tree, or the preferred method here is a sparse table. Why is a sparse table here better? Because there are no updates and it's shorter code, less chance of making some mistake, and also the query is O of 1. That's useful. So because we don't need to update, we can use parse table, which is quicker, easier to code. Okay. After that, we have two more applications. I think we will have just the right amount of time for that. So the longest common substring is again one of the most famous problems using suffix array. Most of these are really famous, so it's very useful to know them. They can come very useful in a lot of tasks, as you will see later. You have, I think, 5 or 6 here. Let me check. 1, 2, 3, 4, 5, 6. So 6 different tasks, 6 different labs. So I hope that you will have the time to do them. They will be very useful to you, I'm sure. Okay, so what is the longest common substring? Well, you have 2 strings and you want to compute what is the longest common substring between them, right? So substring that they both have and is the longest. So what are we going to do? Well, instead, here we might be tempted to like to build separately the suffix array for s, suffix array for t, then maybe go through one and do like a binary search or something. But that is going to be slow and unnecessary. What we're actually going to do is we're going to put something like s plus, we can put like a pound sign. Then we're going to do a T and we're going to do like the dollar sign at the end. So we're actually doing a suffix array for the combined strings. And this is very useful. You will see it in many problems that you want to add different strings and build together the suffix array for them. Why? Well, obviously it's quicker, and we'll see why is this specifically useful here. Why do we want to separate them? Well, we obviously don't want some characters from T to affect our sorting of suffixes in S, right? We still want to have kind of suffixes of S, suffixes of T, just sorted together, but we want them separate in the sense that we will not use any characters from T to sort S. That is why we added this pound sign here to avoid collisions, basically to use T in suffixes of S. So we build the suffix array here of this. And how is it useful? Well, what's the thing that we need to do? Well, now we just need, let's say that this is the suffix array, and I'm going to draw like, these are the lengths of the different strings in the suffix array. And because we know the index, we know whether a suffix is from S or from T. So let's say it's something like this. And also, yeah, these two need to be separate, different actually, pound sign and dollar sign, just to avoid any, again, collisions from that. The same thing, to avoid using any characters from S in T. But yeah, so now for each of these strings in the suffix array, we know whether it's a suffix of S or a suffix of T. So if we want the longest common substring, we're just going to take each 2 consecutive ones, which are from different strings. So let me draw that in a different color. So these two, and these two, and these two, right? These 4 pairs are next to each other and are from different strings. We're only going to compare them. And we're just going to take the maximum of their minimum. So what is the longest common prefix between them? Well, we know that, right? we calculated the LCP array. So that is the length of the first pair, right? So we know the score for the first pair. For the second pair, it's this. For the third pair, it's this. Or actually, it might not be the whole thing, but let's say like this. Then it's like this maybe, then it's like this, and maybe like this. So what is the answer? The answer is this length, because it's the biggest one. That is the longest common substring. As we said, all substrings are found as prefixes of suffixes. So that's why we can do this. Why is it not going to be, for instance, this suffix of s with this suffix of t? Well, we said that all of these, that this is going to be the LCP of these two is going to be the minimum of all of these. So you definitely like won't get the best and the longest if you go further, right? The best LCP you can get are between two consecutive suffixes in the suffix array. So that is why we're only considering adjacent pairs. Okay, and that is it. So the LCP of 3 would here be the answer. And for the last application that we will talk about today is count unique substrings. So the statement is, again, think obvious. We have a string and we need to count the number of unique substrings. So take all substrings, get the unique ones and count them. So how are we going to do this? Well, let's again consider that we have again, we have s and we have added the $sign and we calculated the suffix array. And what are these things? Those are just the length of that. So this is the length of the zeroth of the first suffix. This is the length of the second one, third, and so forth. It's just an sorry, a nice way to visualize it. So we don't have to deal with an actual string, but we can just imagine it. And so on, just like add them kind of randomly. Imagine that they are all different sizes. Doesn't matter, let's say like this. And yeah, we want to count unique substrings. So if we start from the first one, we know that each of its prefixes is unique. By unique, yeah, so just to clarify, unique does not mean we want only the substrings that appear once. We just want to count different substrings, right? So how many different substrings there is. Not unique in the sense that it only appears once. This is important to notice. So just we want to count each substring once. So for the first position, we would add 5 in this case, because each prefix of this suffix, we have not seen anything like it yet. But here, what happens now? Let's say that this first one is maybe ABA, CB, whatever. And the second one is AB, CCCA. Okay, how many have we seen already? Well, how many prefixes of this second one have we seen already? Well, the first two, right? A and AB we have seen already. But all of the other ones are new. right? So how many are we going to add? 6 minus 2, so 4, right? So all of the 6 ones except the first two. Well, how many is it in common? Well, it's actually the LCP between these two, right? Longest common prefix. Those are the ones that we have seen already. Why have we not seen ABC somewhere even more before? Well, because we would not have ABA before it, right? That doesn't make sense. We cannot have something here, ABC, and have then ABA, then ABC. That is not sorted lexicographically, right? So the same goes for later. Maybe we have, let's say now we have ABC, C, DB, okay? How many have we seen? Well, the first 4, right? We have seen it in the previous one, and 4 is exactly the LCP, right? So we see that in each step, it's just the length of the suffix minus the LCP of that suffix. Okay? And what's the, when we add all of that, and that's going to be the case all the way through, when we add all of that, that's going to be sum of lengths minus sum of LCP, so sum of this, which is the sum of lengths, minus the sum of LCP. Obviously, if we have the sum of lengths is 1 plus 2 plus 3 plus all the way to n minus the sum of LCP. This we know that it's n times n plus 1 over 2. And we just subtract the sum of array LCP. And this is the number of unique substrings. Because again, in each step, we're adding all of them except the ones which are common with the previous one. And that is basically all of the most common applications. You will have 6 labs here, and they will have some interesting ones. You will have some between multiple strings, more than 2. Some will be some interesting other things that you can do with the suffix array. There are many now variations of what we're doing here. I prepared some, for instance, in case we had more time. So maybe like, what's the case smallest substring from all the distinct substrings? You can do that very similar to this last thing. Then like, what's the biggest substring that appears at least twice? What's the biggest substring that appears at least k times? These are the different things that you can do with the suffix array. So anything that deals with these substrings, what's the biggest one that appears this many times, that is common between these between these strings, anything like that, you can use a suffix array. You can often use a suffix array for these things. Okay, so that would be it from my side today, unless you have any questions, but yeah, I think that's it.
Sorry, I think that I do not hear you. Do you hear me, Mladen? Yeah.
Yes, I hear you.
Great. I think that something gets wrong and the video is stopped. Okay, everything okay.
Hmm.
So it was the last topic, was it?
Yes, we'll just have the editorial on Tuesday. I think Vladimir wanted to share that today.
Yeah, correct. So we will have a session, one more, not lecture, but we will discuss about some topics, about some assignments. You have difficulties with some of them. I know about that. And the time and date of this meeting we will send you in your emails. So now we can finish our lecture. Yes? Great. So I hope you will do the best in your topics. And I want to remind that on August 29th, there will be a competition for you. And this is a very serious competition because it will show how your topics, how did you understand all the topics, and we will share the results on August 30, and after that we will invite top students to our on-site camp in Baku. And if you have some questions about it, we will share the information tomorrow in our Discord, on our Discord server, and also we will send it to email, and you will find it there. So I hope you will do your tasks. And now we may stop our live stream. Thank you so much. See you on Tuesday. Yes? Great. Thank you, Mladen. It was very interesting.
Thank you. Good luck with the tasks, everyone.
Yes, and please tag our teachers if you have some difficulties. We will try to help you. Okay? Ciao.